Let's consider a structure. For ease of imagination, we have a building. A host of natural and human based sources can vibrate our building. These excitations include wind, earthquake, vehicles, and machinery in some specific buildings. In many instances, vibrations can actually damage the building or its components if the vibration is too strong, or if it's recurring over a long time. Now, one way to enhance our building's performance is to make it stiffer and stronger, but that's too expensive and impractical in some cases. There are a range of energy dissipative solutions available instead that absorb and release the kinetic energy of the vibrations instead of the building absorbing them, which could mean causing damages. Yielding dampers are sacrificial metallic devices that dissipate energy through yielding action. Friction dampers, well, those are pretty self explanatory. Tune mass dampers are counteracting masses that target the building's primary frequency. When the building vibrates, the tune mass vibrates in an opposite direction to in some way pull the building back. There are also magnetorheological dampers that are used predominantly in the car industry. These are viscous dampers where the friction is induced by a highly viscous fluid latching onto the damper piston. And you can pretty much adjust the magnetic properties of the magnetorheological damper to modify its friction coefficient. Active control solutions are actuated devices that impose forces on the building to counteract the vibration motion. Lastly, isolation layers are useful for earthquakes. They are typically elastomeric materials which shift the fundamental frequency of the structure away from the typical 0 to 10 hertz frequencies of an earthquake. They make the building vibrate as a rigid body instead of a flexible one. Now, these are just a list of solutions. Within the field of structural control, there are actually way more solutions than what is listed here. Here's an example. The 432 Park Avenue is a super slender 1,400 foot tower in New York City. The building's width to height ratio is 1 to 15. That's staggering, and as you might imagine, the building will sway back and forth a lot. Now, to avoid this problem and to make the living experience more hospitable to the residents, the structure has two massive tune mass dampers at the top. There's actually a pretty cool video of this tune mass damper here on YouTube that I recommend you look up, and I will actually link to it in the description section. The damper is moving a lot in this video. It's very interesting. This is a picture of me from 2016 standing in front of a tune mass damper. This was a commercial building in Japan that had four massive tune mass dampers at the very top. And in the picture on the left, you can see two of the tune mass dampers, and in the picture on the right, you see a not so tuned gentleman. I've shown you pictures of buildings so far. What you should know is that dampers are not unique to buildings. They are installed on bridges too. These dampers shown here are installed for each of the cables in the Arthur Ravenel Jr. Bridge in South Carolina. These dampers absorb some of the kinetic energy from wind or load-induced vibrations on this bridge. This bridge was designed to resist large earthquakes, and these dampers might have to do something with that as well, I wonder. And also, you heard me right, South Carolina is pretty earthquake prone. Structural control can be broken down into three primary areas. These are active, semi-active, and passive control areas. In short, classification depends on power usage. If no power is used at all, we are dependent completely on the dissipative and mechanical properties of the control solution. And we say we have a passive control solution. If power is sometimes used, we have ourselves a semi-active solution. When power is constantly required for either sensor or actuator use, we have active control. Generally speaking, most control solutions are passive. Active and semi active solutions are emerging technologies that have been studied and used over the last 20 years. In terms of complexity, active and semi active control solutions are most complicated as they involve sensor use and manipulation of the damper or actuator response using control algorithms. So, you may be wondering how structural control is conducted. Well, here's a short response. Excitations cause structures to respond through vibrations. If your structural control solution is passive, your structural response will interact with your dampers to create damping forces, which in turn dissipate kinetic energy for your building. If your structural control solution is semi active or active, your structural response will first need to be detected via sensors, such as accelerometers, let's say. A computer based controller will then generate electric signals in the form of currents to guide how your active or semi active actuator and damper interact with the building. The current, for example, may control the friction coefficient of your magnetorheological damper and how it changes. In terms of what you will need to learn structural control, you need to have a fairly strong background in structural dynamics. You will need to learn some concepts in control theory, and you should know a little bit of numerical integration because in this course I will be predominantly using MATLAB and Simulink, and some of the coding that I will be doing involves some numerical integration. Well, thank you and see you next time.